My name is Fred Blazgan. I'm currently lead engineer for the heat transfer group at Worley Parsons. I'd like to give you a presentation. Hopefully it's a little bit better than what we had Wednesday. We've had some issues, some of the slides we couldn't read, so this is kind of a presentation that's under development, so hopefully it will get better as it continues. So let's go ahead and get started here. First, I'd like to say that this is kind of a group contribution. Just about most of the folks in the Arcadia office in the heat transfer group contributed to this in some form, so I'd like to give them credit. So and unfortunately our clicker isn't working here, so we'll progress through using the mouse. So this is just kind of an introduction as to it's not really related to heat transfer, but it's just a matter of telling you that keep your eyes open. You'll see interesting things where you are. So wellhead in the Gulf of Mexico, one of the operators up in Alaska gave that to me. So again, it's just a matter to keep your eyes open and you'll see interesting things. It's a whale cruising by. It's about 3,000 foot depth. So I thought that was kind of neat. Okay. Yeah, that's what I'm looking for. We always start out with a safety moment, so this is some things to consider. This is a list of 5 safety items graded by levels of incredibility. So we'll see what this was 5th place.
Oh my God.
And they were just trying to, their boss told them to move those upstairs, so they found a way to do it. 4th place. Almost as good. 3rd place. Somebody doesn't understand what's going on. 2nd place. Barefoot on a ladder in water using an electric device. So, in fact, they just had another fatality down at Texas City. So, electrocution isn't too pleasant. And the winner. So that's okay. Again, my name is Fred Blazgan. I'm currently lead engineer for the heat transfer group, and we'll get into the program. This is a tentative schedule. It hopefully we'll be able to hold to this, but we'll play it by ear. And if somebody needs to take a break or needs some water, give a yell and we'll take a brief intermission. We'd like to have about a 10-minute break, so after that, please head back. Heat transfer organization will basically cover the organization, our departmental interrelationships, workflow, tools and resources that we have. What we do, basically we are a support group to project. We will basically select different types of equipment. We will perform estimating. We will specify equipment requirements for equipment as necessary. We will requisition equipment for a project or develop pricing for budget or budget pricing for proposal type work. We also may include, depending on the project direction, is we would do a bid analysis. We would review vendor data, testing and troubleshooting if required for equipment that's in the field, and we would do support thermal analysis for systems that are currently in use. The types of equipment that we handle, we would have heat exchangers. That could be multiple types: shell and tube, multi-tube, hairpin type exchangers, plate and frame, spiral, compa block, many types. We'll cover them in the presentation. Air-cooled heat exchangers, which are more of the conventional type that you're used to seeing at the facilities. Fired heaters. We have heat recovery steam generators and also waste heat recovery units, which I had not updated this slide, so that needs to be done. We'll cover flares, and we do quite a bit with specialty packaged equipment. In addition, we will do preheaters. This would be like air preheaters for fired heaters, for combustion air preheating. We will do refractory analysis for thermal distribution inside, as in sulfur condensers. We work with the materials group to analyze those. We deal with scrubbers, either the wet scrubbers or dry for flue gas emissions mitigation. We do multiple types of filters, the package type, the packed bed type. We will do stack emission studies, and we will do attemperators, which are also known as desuperheaters. Again, in addition to that, we will do boilers, burners. We're currently doing a burner retrofit for a heater on the North Slope. We'll do condensers, although we have not done any of those recently. That's typically power work. Cooling towers, we don't have many of those on the North Slope, although we will probably be looking at some of those for the Chevron project at Richmond if any of you are working on that. We get into deaerators and degasifiers and dehydration and dryer packages. Just as a show of hands, how many are in process? Okay, how many in the civil? Okay, instrumentation? Okay, rotating equipment? Okay, all right. Okay. Some of the items will, unfortunately, we have a good package this time for instrumentation, but it's in the handout there, so when we get to that, we'll discuss it briefly. This is the current arrangement for our org chart under the mechanical group led by Gary Ehlers. The heat transfer group is shown there. We have the basically my position, current position. We have the project lead engineers, and then we have the support engineers, which are these are basically the new graduates at this point in time. Hopefully, we'll have some more as work the load increases. This supposedly is my title. However, right now I'm involved in more project work than the administration or organization. I do the technical reviews, but it's primarily support for projects. These are the staff heat transfer engineers, and again, everybody is pretty much heavily involved in project support at this point in time. This reflects an older organization where we had a more structured department. This is probably a more typical representation of what we are all doing here. We're all supporting multiple projects, as noted here. Some of us will act as a lead, others will act as support members for a project. We basically follow the project procedures. try to stay within the budgets and schedules. And the main point here is the coordination with the other disciplines. The individual heat transfer engineers, these are some of the new people we have in the group. They assist the leads. We serve, they will also support multiple projects. Again, they contribute to the workflow by following up on issues that the lead engineer has assigned them. Departmental interrelationships. This is a big issue. The more we follow this, the more life is pleasant for everybody. This kind of shows you how all of the different disciplines interface on a piece of equipment. Here we have a fuel gas skid for a fired heater. You can see we have the input from electrical, instrumentation, materials group. They basically will define the types of metallurgy that we use for components. Structural, this is a obviously very simple structural base, but how that fits into an overall package is really the main issue. And then piping, we always need to coordinate with them for the integration of packaged equipment like this and how we fit into their overall system. So this is pre-current attire with the neckties, etc., but it kind of shows you the idea of how we communicate among ourselves. This is kind of an example of trust. One day you're holding the target, and the next day you're at the other end of the target, shooting the gun. So the whole idea is to work among yourselves and share information and keep the other person out of trouble. If you know something that's going on that they need to be aware of, tell them about that rather than letting them find it by surprise. That way it makes all of our work a lot easier. This is in your handout. I'm not going to try to go through it here. If you want to look at it, it basically shows how we get inputs from all the projects through the disciplines and what our outputs are. This is kind of recaptured in the following slide. We basically will receive information from, actually this is an overall summary of our work process steps. We receive information, and each of these bullets or items is covered in the subsequent slide. So again, we receive information, estimate equipment sizes, conduct economic feasibilities, prepare heat transfer specs and data sheets, rate exchangers, prepare inquiry requisitions, analyze bids, issue purchase requisitions, and perform post-work order issues. So item 1, receive information. Primary sources are from the project based on the job scope and client specs. Obviously, the next step after that is from process. We will receive process data sheets, heat and material balances. From those, we're able to do our work in terms of preliminary sizing of equipment. From mechanical process, we'll receive equipment data. Again, this kind of reflects an older structure. Process is now fully integrated, so process people are doing both the mechanical process and process work. So this is kind of an intermediate step. Maybe we'll pull that out in the future on a future slide. Material applications groups are very important. Based on the PFD that we receive from process, they will in turn add their specific material requirements for each component in that system. We will make sure that we are aware of those materials and implement those on our data sheets to ensure that whatever is required is on the heat transfer data sheet. In terms of estimating equipment, we will determine either by experience or by previous jobs, we will prorate to come up with approximate costs for equipment. With the current material market volatility, that's very difficult to do, especially if you get into alloys. Our preferred method on that is to talk with some vendors that we deal with frequently and get an updated material cost from them, or even better, an estimated cost for that particular piece of equipment. Generally, because of, again, market volatility, usually it takes about 3 to 5 days to get a turnaround from the vendors. This would apply to just about all equipment items. The larger and more complex the equipment, the longer it takes. Packaged equipment is kind of interesting. That is always a difficult issue. There are a lot of inaccuracies involved in the estimate, so usually we try to get like plus or minus 30% for a package. We'll conduct feasibility studies. In some cases, there may be more than one way to perform a process, scheme. We might look at shell and tube exchangers using a utility cooling loop, or we might look at an air cooler loop. With shell and tube exchangers, generally we're conserving energy, whereas with air coolers we're rejecting heat to the atmosphere, so it cannot be recovered. And there's also utility costs with respect to the electrical load from the coolers. We will go through material selection optimizations. We've just completed that on the New Zealand refinery. We had about 6 different material options that were reviewed, and I think we finally come to conclusion on which is the recommended process. In terms of logistics, that's a big issue on the North Slope because everything has to be trucked in unless it's a sea lift module. Generally, we're restricted to about 14 foot wide, approximately 60 foot long, and the weight might be upwards of, I think we're on the order of 80 tons right now that they can transport by truck. For like the GPP project, who some of you may be involved with, that's going to be a sea lift, as I understand it at this point in time. We will take heat transfer specs. We'll start out with client specifications if they are available. Otherwise, we'll base it on industry standards or previous specs that we've developed for that particular type of equipment. Within the specifications, we'll incorporate the site conditions, any seismic or wind conditions that are applicable, soil conditions, utilities that are available to us, and we will also incorporate area classifications, which are a fairly significant cost impact to electrical components if it's explosion proof, if we have fuel gas in the area. What we will do for exchangers, typically we will rate an exchanger. What that means, we will take the process conditions, the heat material balance, and we will convert that into a physical size for a heat exchanger which will perform the required process duties. That would apply to both air coolers and shell and tube exchangers. Multi-tube exchangers, which we will cover later, we will do a preliminary sizing. The vendor will do a final sizing based on his proprietary designs. We do not rate fired heaters. As a preliminary design, we will check rate them. Again, what's noted here is for shell and tube exchangers, we'll use HTRI. Air coolers will also use a program within the HTRI suite. For fired heaters, we have a program called PFR. Boilers and heat recovery steam generators and waste heat recovery units, typically we will go out with a vendor sizing, and then we'll do an in-house check to confirm that we agree with the surface areas that are being provided. With those process data sheets, the client specs or our heat transfer specs will develop an inquiry package. It will typically be segregated by type of equipment, either carbon steel equipment, as all carbon steel shell and tube exchangers, or alloy exchangers. They would typically be put into a separate inquiry package. We would have multiple items within that, which would be shown on the deliverable item list. We would include the technical documents, requirements, and notes. Basically, that will tell the vendor what he has to adhere to. Any special requirements would be listed on the technical notes. We would also have vendor drawing requirements, which tells him what he has to provide to us in the way of documentation to ensure that we have adequate documents to review once he's been given an award. And he also has to submit an inspection plan, which would identify the steps of NDE that he would perform to ensure that it met our requirements. Excuse me while I have some water here. Anybody has a quick question during the presentation, please jump in, raise your hand, and if it gets into detail, we'll address it after the presentation. The technical bid analysis, basically what we do, we will take all the vendors that are bidding on a particular type of equipment item. We will compare them to ensure that they are meeting the requirements that we have specified. We will compare them based on the performance, the materials, any particular details that might be different between them, to see if that has an impact on our evaluation. Ideally we are able to review commercial terms such as price and delivery. On some projects we are unable to do that based on project direction. It is a major assistance in the evaluation, and in some cases it is critical because some vendors' proposals will have options, and unless the buyer is aware of which options we want, there can be a problem in terms of what he thinks he wants to buy versus what we know we need to buy. So we are able to make a technical recommendation. In some cases we'll have to say final decision is to be based on commercial terms. We need to be very careful that we identify which options are the preferred options, so that again that is considered in his final price buildup. Once the vendor has been selected, we will issue a purchase requisition which will identify the specific items that this vendor is providing to us. If there were material options, we'll capture those. We'll update the technical documents and requirements. In some cases, they might not apply if there's a change to the requirements that the vendor is unable to comply with, or there's a conflict between the specifications and what the vendor is proposing. That obviously has to be worked out between project and the client to ensure that if it's a deviation, and that would have to be signed off by the client to ensure that even though the vendor proposal does not comply specifically with a spec issue, it is still acceptable to the client and to the project. The inspection plan would also be updated to reflect what the vendor is going to provide to us. Post-work orders, that would basically consist of the vendor drawing review. This is a very important issue because all the disciplines get a chance to look at what the vendor is proposing at this point in time. Piping will want to look at all the nozzle connections. Structural will want to look at the saddle base. Instrumentation will want to look at any interface points that they have. As an example, we will have vibration monitors on air coolers. Sometimes there's an instrument preference for that device. So this is an opportunity, and also on electrical, that's another big issue where we have classified areas. We need to make sure that all the disciplines are aware of what this vendor is going to provide, and if we need to augment that, or if there's a client preference to a design upgrade, which happens very frequently, we need to make sure that all the disciplines are involved or knowledgeable of that. Another very good source of information is the coordination with the field inspector. They are basically our eyes and ears, and if you have an opportunity to talk with them, you will learn a lot. If you have an opportunity to go on a prefabrication meeting, either at the initial fabrication kickoff, or later on, if there are design issues that need an engineer's hands-on view of what's going on. Document and closeout and shipping will be involved in that, making sure that the equipment is properly prepared for transport. If you have equipment that you're handling, this goes for either heat transfer, rotating equipment, or any other type of equipment item that you're personally involved with or responsible for, call the vendor and ask them for photographs. That's one reason why we're able to present photographs here, that you'll find that if you don't do that, you'll have secondhand knowledge of what was actually provided to the field. So my recommendation is, once you are handling an equipment item, ask for photographs of what you're actually working with. This is an example of checking at each work step. So we try to do that among our group. This also comes up in interdiscipline coordination. If you see a mistake or an obvious error that another group has developed, it's always nice to give somebody a heads up rather than letting it go to the client, and all of a sudden you find out that it's a big surprise and nobody likes that. So, work among the disciplines to make sure that this doesn't get to the client. Another interesting point is make sure you write knowing who your readers are going to be. As you can see, the write for free help. Obviously, if you're illiterate, you can't read. So make sure whatever you present from your discipline, that is written to the user, and that they are, that it's clear, clear passing on of information with documentation. These are the tools that we have in industry tools that we have in heat transfer. We have the industry standard resources, and I'm sure all of you are aware that most of these are available on the IHS website. When we switch to the Worley-Parsons, the new web page, I have not been able to find that, but this is based on an old link. So if some of you, if you don't know where it is, please ask either IS group or come to us, and we can send you a shortcut to the IHS website. As noted, we have API as a major resource. In addition to ASME, we deal with Section 1 powered boilers, Section 2 materials, Section 8 typical for Section 8 Div 1 vessels, which applies to heat transfer type equipment. We have the NFPA, National Fire Protection Association, for boilers and combustion systems. We also have standards for the ovens and furnaces. One of our primary sources is TEMA, which stands for Tubular Equipment Manufacturers Association. They basically set the industry standard for shell and tube type equipment. Multi-tube heat exchangers are not applicable to that particular association standard. They're kind of a little group on their own, but they do have to comply with code and other materials requirements. These are our in-house tools for heat transfer. We have the HTRI suite, which covers shell and tube, air coolers, fired heaters. It will handle kettle-type reboilers and other types of shell and tube exchanger designs. Aspen is a very good resource. We've used that on a Drill Site 1J project, mainly because HTRI did not really appear to handle emulsion properties correctly, so it was felt that this was a better design for the shell and tube exchanger. And that's noted here with emulsion streams. In that case, we had gas, water, oil as an emulsion, and we had viscosities anywhere from 1,000 centipoise coming into the unit, and it was considered by